Hi, I'm Natalie, a rising junior at Carlmont High School. This summer, I received the opportunity to return to the University of Washington's Chemistry Department in Seattle and tour the Cossairt Lab. The Cossairt Lab develops nanoparticle nanotechnology, technology designed on the near atomic scale. Nanoparticles are extremely small particles that are on the nanometer scale. They can be used for paints, sunscreens, medicines, and so much more. So the Cossairt Lab is hoping to improve on their efficiency and availability. One example of nanoparticles in everyday use are QLED TVs. The Q in QLED stands for quantum dots, which is a type of nanoparticle used to build TVs with better color and very high energy efficiency compared with previous TV displays. Quantum dots can also be used for hydrogen fuel cells that can be used to power cars or for portable or emergency power. Quantum dots are a spherical group of atoms only a few nanometers wide. Many have a core shell structure, which is important for their optical properties. Quantum dots can either be used for light emission, meaning they can absorb light energy and emit it back out, or photocatalysis, meaning they can convert light energy into chemical fuels. Quantum dots have a series of energy levels which electrons can move between. When working with quantum dots, scientists typically focus on the band gap between the filled and empty energy levels. When light reaches quantum dots, electrons can absorb the light energy and move to a higher energy level. From here, the electron can release a photon with energy equal to the band gap between the empty and filled energy levels. Depending on the amount of energy released, different colors are emitted, so the colors emitted by quantum dots are dependent on the size of the band gap. This can be affected by either the size of the quantum dots or the elements used to create them. In QLED displays, this is how quantum dots create better colors that cover a larger area of the color spectrum. However, instead of releasing photons, it is also possible for the excited electrons to catalyze a reaction. This is called photocatalysis. Part of the Cossairt group develops quantum dots for light emission and photocatalysis. They are working to improve the efficiency of quantum dots. I shadowed Michaela, a graduate student who tests the current response of quantum dots to measure their efficiency as photocatalysts and to make sure that as little energy as possible is lost during energy conversion. The Cossairt Lab works with materials which are very oxygen sensitive, and many of which are pyrophoric, meaning they can suddenly ignite if they are exposed to air or moisture. Because of this, many precautions need to be taken. Michaela puts the quantum dots in a specialized glove box, which contains no air or moisture, and then takes a cyclic voltammetry measurement when they are in the dark and when an LED is shown on them. From this measurement, she can determine how quickly light energy is converted to chemical energy. I additionally shadowed Florence, a graduate student who is also working to improve the efficiency of quantum dots. However, unlike Michaela, Florence works on the synthesis or production of quantum dots. Quantum dots are created using a cation, anion, a solvent, a ligand, and sometimes an additive, which can improve the quality of the quantum dots that are synthesized. The process of creating any nanoparticle is very complicated. Florence showed me how to create indium phosphide quantum dots. A precursor is a substance from which another substance can be formed. The precursor we used for the cation, indium, was indium iodide, and the precursor for the phosphorus was tris diethylaminophosphine. We additionally used allylamine as both a solvent and a ligand. Ligands help maintain the size of the quantum dots and help them dissolve better in the solvent during a synthesis. The reagents were prepared in a glove box, then the indium iodide and the allylamine were moved to a fume hood which contained a Schlenk line. A Schlenk line is a set of glass tubes filled with nitrogen to prevent air and water from affecting the reagents. The Schlenk line is also connected to a vacuum, which could suck out any air from the glass tubes. It was also connected to a little glass bubbler with liquid mercury to check the pressure of the nitrogen. The mercury bubbled whenever nitrogen was pumped through, so whoever was performing a synthesis could know that the Schlenk line was working and didn't have a leak. We then brought out some glass from an oven, which is used to remove any moisture from the glass. We used a 3-neck round-bottom flask, which we added the reagents to, a thermowell to hold a thermocouple, which measures the temperature, and condensers, which connected the 3-neck round bottom flask to the Schlenk line. We assembled the glass using grease, which acted as a seal to prevent any exposure to air during the synthesis. On the Schlenk line, we set up some liquid nitrogen traps, which would freeze any solvent to prevent it from getting sucked into the vacuum while air was being pulled out. We added in the reagents to the 3-neck round bottom flask, then pulled vacuum or degassed the system to remove any air that could have gotten in while we sealed the setup or transferred the reagents from the glove box. After heating it up to a high temperature, we injected the precursor for the anion. This is called a hot injection synthesis, and it is how many quantum dots are made. The solution changed from yellowish to a deep red, signifying that the synthesis had finished. Another part of the Cossairt group conducts research on using nanoparticles for catalysis, or helping to speed up chemical reactions. Some of the potential applications of nanoparticles for catalysis include removing CO2 from the atmosphere, nitrate reduction, or recycling wastewater from fertilizer, and hydrogen evolution, the production of hydrogen gas for fuel. Nanoparticles can form bonds when coming in contact with certain molecules, and sometimes can act as a catalyst for chemical reactions. Nanoparticles are good for catalysis because their surface area to volume ratio is really high, which means there are more atoms available for molecules to bond to on their surface. Scientists can control the nanoparticle bond strength, which affects how good of a catalyst it is, and therefore they can also control the products of a reaction. There are a few factors which can affect nanoparticle bond strength: its structure, the elements it's composed of, and its ligands. I shadowed Emily, a graduate student who works on electrocatalysis with nanoparticles, and who showed me the process of creating and characterizing nanoparticles. She is working on finding a way to create nanoparticles with more earth-abundant and cheaper materials for clean energy conversion. The process to create the nanoparticles was very similar to how I created quantum dots with Florence, except for a change in the metal or cation precursor. The precursor for the cation, nickel, was nickel chloride. The precursor for the anion, phosphorus, was also tris diethylaminum phosphine. We use alanylamine as our solvent again. We set up the Schlenk line and the liquid nitrogen traps. The procedure of degassing, vacuuming, and heating up the solution was similar. The solution went through several color changes, turning from yellowish to reddish-brown to black. Once it turned black, we knew that the nickel cation had been reduced, and the synthesis was complete. After synthesizing the nickel phosphide nanocrystals, we will test its ability to catalyze various electrocatalytic reactions. Emily also showed me how X-ray diffraction, or XRD, is performed. XRD is a technique that is used to collect data on crystalline structures to confirm their atomic arrangement, and whether or not the desired product was made successfully. During X-ray diffraction, X-rays are shined on the sample, and then diffracted in different directions. This can be recorded as a spectrum, and can be compared with known data on the sample to see if the synthesis was successful. The Cossairt Lab hopes this research will yield new breakthroughs that will expand the utility of nanoparticles for impactful application. I had a really fun time learning about the Cossairt Lab's work to increase the efficiency and availability of quantum dots. Thank you to Emily, Florence, and Michaela for showing me your work and for making such a complicated matter so accessible. And thank you to Professor Cossairt for letting me tour your lab.